Okay, so picking up where we left off, and if I can have Kennedy just turn off that front light switch, please. Thank you. Okay, it was not until the late 1700s, obviously, that we got all of this idea that atoms might exist. Okay, the reason people thought that atoms might exist was because they had actually been observing chemical reactions for the purpose of learning something, as opposed to what the alchemists were doing, which was try to make gold. Okay, I mean, basically, if you're trying to make gold and it doesn't happen, you don't really care why. You just move on to something else. Okay, whereas with chemists, that's not their purpose. Okay, so they were watching what would go on, and they could actually almost envision in their mind the movement of pieces of one material to join with pieces of another material. Okay, and that's why they kind of led them to the idea that matter might be made up of these small indivisible particles that Democritus had talked about. Okay, so we said here with Dalton's atomic theory, the first point of it was everything's composed of these tiny things called atoms. Okay, atoms of the same element are identical. We talked about that yesterday as well. Okay, and then of course redundantly, atoms that are from different elements must be different. Okay, atoms of different elements can combine with one another in simple whole number ratios. We said that whole number ratios part was important. Okay, you never have a molecule that contains half of an atom. Okay, because if you have half of an atom, you've split the atom. All right. And lastly, chemical reactions occur when atoms are separated, joined, or rearranged. Okay, so in a chemical reaction, and that was just what I was about to start drawing for you there, okay, we see this movement of materials around, but we don't see the creation of anything new. Okay, the example I gave you yesterday was this one. Okay, the reaction of octane, which is the active ingredient in gasoline, okay, reaction with oxygen to produce carbon dioxide and water. Okay, what we have to realize about a reaction is I'm not creating anything. Right? And I'm not magically turning one element into another element. I can't do that. Okay? Atoms can't be changed. Who they're paired with can be changed, but the atoms themselves cannot. And that's what we see in a chemical reaction here. I start out with carbon, I start out with hydrogen, I start out with oxygen. And on the other side, I still have those same elements. That hasn't changed. Okay, who they're paired up with has changed. Okay, the appearance and physical and chemical properties of the things I have changed. Okay, but other than that, I still have the same basic materials that I started with. All right, does everyone follow me there? Okay, this is where the alchemists had the idea wrong. They saw that when they lit something on fire, it turned into, like, black stuff and gas. And they went, well, I'm a magician. Look what I did. I turned this solid object or a liquid thing into nothing. All right? But in actual fact, that's not what they were doing. Okay? They were rearranging the atoms to have new partners, okay, and create stuff that, well, not create stuff, but produce stuff that had different physical properties. Instead of being a liquid, they now had two gases. Okay, because it's water vapor, not liquid water that would be produced here. All right? Does that everyone kind of understand that? Okay, other types of things, you could have a reaction like this one, where we take water, and if we run a very strong electric current, essentially an arc of electricity through it, we produce this. Okay, do I still have the same elements I started with? I only have hydrogen and oxygen. That's what I started with, that's what I finished with. All right? But I go from having something that was a liquid to having two things that are gases. Right? But they're still the same things that I began with, at least from an element perspective. All right? That's the thing we have to realize about the fourth point of the atomic theory. Okay? Is that a chemical reaction will not create new material. It will rearrange, it will alter, it will pair up differently, okay, the material you started with. All right? So we should never have a reaction that essentially looks like this. Okay? Because somehow I produced lithium by reacting hydrogen chloride and sodium hydroxide. Somehow I got lithium out of that. Like, it just doesn't happen. Okay? I can't magically produce a new element if I didn't have it to start with. Okay? All right. Questions on that part? Okay? I would say, guys, that in your notes you need to make a point of those 4 points. Okay, it's not so much that I'm gonna, ask you to write down the 4 points of the atomic theory. Although I might do that on a quiz, just because it's kind of a simple recall thing. But it's certainly not something I would do on an exam. Okay, what I'm concerned with is, do you understand the implications of these points? And that's what we've been talking about here. All right, like I could ask you, a question where I wrote down a reaction like this one here, and I would say, using what you know of the atomic theory, explain to me why that can't happen. Okay, or what would Dalton say about this reaction? Okay, and then you would have to go, well, Dalton's atomic theory said that in a reaction you don't make new stuff, you just separate, join, and rearrange things, and you're applying and you're showing me you understand that. Okay, does everyone follow me there? Okay, so Dalton puts this stuff on paper, and immediately what people want to know is, okay, what do atoms look like? You said they're really small. What do they look like? And Dalton's answer is, I don't know. They're really small, and I can't see them. Well, people don't like answers like that because it seems dodgy. It seems like you're trying to get out of explaining something. Okay, so he said, it would be logical that atoms should be a sphere. Spheres occur everywhere in nature. Planets are spheres, stars are spheres. Okay, everything kind of makes this spherical shape kind of by nature. So let's say they look like a sphere. People were fine with that, because they didn't know any better. Okay, things were made of tiny little spheres. They could deal with that. All right. The reason that this didn't hold on very long is this doesn't explain a lot of the other behaviors of matter. Okay, what is it missing? What is the solid sphere model that Dalton came up with missing that we know now exists? Electrons, protons, neutrons. Okay, all that kind of stuff. This doesn't explain any of that. Okay, but for the rudimentary purposes of saying when you pair things up, I can represent them with little balls. Okay, that's fine. People can deal with that. Okay, all right. Problem is that other people started doing experiments where the results didn't agree with atoms being a solid sphere. Okay, one of those people was a guy named J.J. Thompson. He was doing experiments with what's called electrochemistry. Okay, and he found that some reactions could produce electrical current. That's where we get wet cell and dry cell batteries from now. Okay, same kind of technology. That couldn't be explained by the solid sphere model. Where was this electricity coming from? It's not just magically being created. So he said, it's possible that on the surface of Dalton's solid sphere, there are little electrical charges. And they're very loosely embedded on the surface. So they can fall off. And if they fall off, they can make a current that I can measure in this reaction, and that kind of explains where this electricity comes from. Okay, everyone kind of follow me there? Problem is that atoms are electrically neutral. So if you're going to have little negative charges embedded on the surface, you also have to have positives. Okay, so what he said was, we'll say the solid sphere is positive, and the little things embedded on the surface are negative, and we're going to call them electrons because that's what makes electricity. Kind of made sense. All right, so that was J.J. Thompson's model. He called it the plum pudding model. Okay, and it explained, at least in a acceptable way, where these electrical currents could come from in a chemical reaction. Okay, so this is right at the turn of the 20th century. The turn of the 20th century, physics and the study of atomic physics is really starting to move forwards. Okay, we've got people that are studying radioactive materials. Unfortunately, they don't study them very long because they get sick and die at a very young age because they don't understand it's bad for them. Okay, Marie Curie would be an example of that. Henri Becquerel would be an example of that. Okay, people that studied all this stuff and unfortunately, okay, it killed them. But their discoveries didn't fit with this model. Okay? Why would something be radioactive if it was just a solid chunk of stuff with little electrons embedded in it? So people started coming up with other kinds of ideas. Okay? They said, well, if other pieces of an atom can be lost or altered, then there must not be the solid sphere, there must be other particles. Okay? And they came up with, maybe it's the solid sphere, but I've got things that are positive, things that are neutral, things that are negative. It didn't really work because it ended up being too heavy. Okay, didn't have kind of the right shapes and things like that. So they started looking at maybe the atom is composed of many small particles, okay, and they're kind of joined together somehow, or maybe some of them float free, okay. That would better explain how electrons come off as opposed to being stuck on there and just falling off. Okay, maybe they orbit like planets around the sun. People had all kinds of ideas, and they were all reasonable, and there was really no way to prove one or the other, okay, at least at that point, because no one could see atoms. Right? So what ended up happening is a bunch of people did experiments where they were testing the masses of certain amounts of things. And by doing that, they were able to determine that some atoms have more neutrons than they have protons, because that idea had been kind of accepted. And so they were getting an idea of the structure. Certainly Dalton's solid sphere and J.J. Thompson's plum pudding were out the door already. Okay, this discovery of atomic physics and development of that, those things were out the door. Okay, but the biggest experiment, okay, was by a guy named Alexander Rutherford. Okay, sorry, Ernest Rutherford, not Alexander Rutherford. Ernest Rutherford. Okay, he wanted to prove how big the nucleus of the atom was. Because at this point, people were still arguing, atoms are not very much empty space. The electrons are very close to the protons and very close to the neutrons. That's why solids are solid, and liquids, they're further apart. That's why liquids can change the shape or change the shape of their container, okay, and things like that. And Rutherford was actually in that group. He believed that atoms were very big. Right? So he set about trying to prove how big the nucleus of an atom really was and how close the electrons must be to it. So he set up this experiment here. He took essentially like an X-ray machine, okay, source of alpha particles, and he took photographic film. Now I know you guys are of the generation where you've probably never used a camera that actually had film in it. Okay, how many people have actually used a camera that had film in it? Okay, some of you. Okay, so photographic film works like this. It's got chemicals embedded in the cellophane, okay, and when you expose those chemicals to light, they react and they change color, they expose, okay, they become bright spots. So what he said is, I'm going to set this up, and of course anywhere where these alpha particles hit the photographic film, there'll be a little bright dot because the film will be exposed. Okay, it's the same way they do an X-ray, if you've ever had an X-ray. Okay, you stand in front of the X-ray machine and they slip that thing, okay, in front of you, and then they shoot you with X-rays, and the X-rays will bounce off of your bones, but they'll go straight through your soft tissue. Okay, so what essentially happens is the photographic film only gets exposed where your bones are, because that's the only place where the stuff gets through or gets bounced back to the photographic film, and the rest of it goes through. All right. So he had the same idea here. What he did is he put a thin piece of gold foil in the middle of this apparatus. Okay. He said, because I believe nuclei, and the nucleus of an atom, is really big, what's going to happen is I'm going to shoot these alpha particles at this piece of gold foil, and they're basically all going to bounce back. So I'm going to get exposures, okay, kind of all along these areas here. I'll have little dots all over the place, okay, and I might have the occasional dot, on the sides. But basically these things won't get through because this is a solid and stuff can't go through solids. When he ran the experiment, the results were the exact opposite. Most of the particles went through. Okay? You imagine shooting particles, okay, essentially just light, all right, but really small beams of light, okay, at a solid object and having them get through it. All right? His analogy was it was like shooting a 15-inch shell at a piece of paper and having it bounce back. Okay, it was just weird. It was really strange that this had occurred. So the diagram he drew is that atoms have essentially a wide area, but the nucleus is only this big. Okay, so the protons and neutrons are really, really small. The electrons are even smaller, okay, but the electrons encompass an area around the nucleus that's large, right? But because electrons are so small, that means the atom is mostly empty space. Okay, that's why the particles, many of them anyway, got through. Some of them did hit a nucleus, and they would get bounced or deflected or whatever, and those are the ones that we see kind of over in these areas that got deflected. Okay, so his experiment proved unequivocally the existence of the nucleus and the size of the nucleus. Okay? This was like a crucial experiment in atomic physics that allowed us to develop all kinds of technologies thereafter. Okay, I would say Rutherford is probably second to Dalton the most important guy, okay, in terms of the history of the atom, because he proved what essentially it looked like. Okay, so I would say he's pretty important, and understanding what his experiment proved to us would be a pretty important thing. All right, later experiments by a guy named Niels Bohr showed that Rutherford's experiments and his results were mostly correct. The problem was now we know where everything is. Where are the electrons? What are the electrons doing? And so that became the next area of argument. Okay, a lot of people were in Niels Bohr's camp. They believed it's logical that they should orbit the nucleus like planets orbit the sun. That way they won't run into each other. They'll all be different distances away. Like charges like charges repel and opposites attract, so that's the force that'll keep the electrons orbiting, just like gravity attracts planets to the sun and keeps them orbiting, and it all kind of made sense. People like that. It was logical. Okay? The only issue with this is it doesn't allow for electrons to gain and lose energy, which we know they do. Okay? How many of you have a watch dial that if you put it in the sun and then put it in the dark, parts of it glow? Okay, fluorescence. Okay, you guys heard that term before? Right? Okay, fluorescence happens because electrons gain energy. They get excited and they move from energy levels that are close to the nucleus to energy levels that are further away because they speed up. And the faster you go, the farther away from the nucleus you have to get. Okay? Bohr's model couldn't really explain that, because if they moved around like that, they might run into each other. And the reality is, they probably do. Okay? So they would move around, they would move to these higher energy levels, and then they would fall back down. When they fall back down, what do they give off? They give off light. They give off energy. Okay? And that allows you to see that kind of glowing phenomenon of fluorescence. This is also the way plants make energy. This is the power for photosynthesis. Okay? Electrons in the chlorophyll molecule get excited, they move away from the nucleus of the atoms that they're on, and then as they fall back down, the plant harvests that energy in order to separate carbon dioxide and carbon from oxygen and carbon dioxide, and separate water and make sugar. Okay? That's the source of energy for plants. So it's a big deal. It's a big discovery that this could happen. Bohr's model didn't really explain that. That said, we still use Bohr's model as a snapshot picture of what an atom would look like. If we took a picture of an atom, we would probably see something like this. If we had a video of an atom, that would be different. Okay? This is a moment frozen in time, whereas de Broglie's model is more, I'm watching the atom, and electrons are going all over the place. Now, it's not completely random. There are areas where you'll find electrons generally, okay, but they can move up and down and around, okay, the nucleus, and that's what de Broglie found when he was studying, okay, the phenomena of fluorescence, photosynthesis, and things like that. Okay, is that sort of making sense? Okay, take a step backwards here back to structure of the atom. In the nucleus is where the protons are and the neutrons are. The number of protons is what determines the physical properties of an atom. Okay, that's why we have a periodic table arranged the way it is. Right? Hydrogen has one proton, and hydrogen is a gas that has an extremely low melting or extremely low boiling point, extremely low freezing point, okay, things like that. Your physical properties are determined by the number of protons. The size of an atom is determined by both the number of protons and the number of neutrons. The bigger an atom is, generally the more neutrons it has. Okay, so we were talking yesterday about something like uranium. Okay, there's different kinds of uranium. Right? There's the most common form of uranium called uranium-238. That's the stuff we use in nuclear reactors. Right? It's got 92 protons, but it's got 150-some neutrons. So it's very big. Here's the problem with that. The bigger an atom gets, the more positively charged protons are stuck in there. And the harder it is for an atom to be stable. Because what do all positive charges want to do to each other? They want to repel. Okay? Now, if you've got a small atom, for some reason it doesn't seem to be as big a deal. But the bigger an atom gets, the smaller, the weaker that intra-atomic force is that holds it together. Okay? So big atoms tend to also be radioactive. Right? So basically everything you see down here, okay, and the bottom two rows of your periodic table, okay, these are all atoms that break down spontaneously in nature. Right? And it's simply because the bigger an atom is, the less stable it becomes. Now, we can use that because there's a lot of energy in atoms that are trying to stay together. If you break them apart, you release that energy. What do we call that? When you split an atom. Starts with F. Fission. Fusion is when we force them together. Similar process though. The same energy is essentially being released. Okay? So fission is easier. It's dirtier, but it's easier, as is the case with most things. Okay? So in a nuclear reactor, essentially what you have are fuel rods. Okay? They're exactly like they sound. They're a big metal rod. Okay? And embedded on the surface are fuel pellets. These pellets are made of enriched uranium. Right? What we do is we lower those rods, okay, into the path of a beam. Okay, and this beam has got, you know, neutrons and things like that in it that are large enough that when they strike these fuel pellets that are full of unstable atoms, the atoms break. Right? And when they break, they release large amounts of energy. Not a single atom, mind you. Okay, you split a single atom, you wouldn't even notice it. Right? But when you split a lot of them, okay, you get a lot of energy being released. So that's essentially what happens. Now, you obviously don't want that reaction to run away on you. Okay? Well, some people do. We call that a nuclear bomb. But that, okay, this is a controlled reaction. Okay, so we cause these atoms to split. Okay, and usually this process occurs in a big water bath. Right? What happens to the water? It heats up and it turns into steam, and the steam turns a turbine. Okay, that's how we generate power using electricity. Okay, it's actually just a steam turbine in the same way that burning coal makes steam and turns a turbine. Okay, this just uses a different source of energy. Obviously, it makes a lot more energy for the mass of the fuel you use, okay, than you would by burning coal. Problem is that the waste products are a lot worse. Okay, I mean, carbon dioxide's bad, don't get me wrong. Okay, but you know, the waste products of a nuclear reactor are also very bad, and you can't just, you know, dump them in the street. You don't want to turn green and glow in the dark. Okay. All right. So that's kind of how the splitting of the atom works. If you're building a bomb, it's not actually all that different. I'm going to show you how to build a nuclear bomb. It's perfectly safe to do that because you could never possibly get your hands on the stuff you need for it. Okay. So what you have here is a very poorly drawn octagon, but essentially that's what you make. You make a shaped charge where all of your explosive material, so this would be like plastic explosive, C4, really primitive ones might even use something like dynamite or TNT. Okay, they make this whole area, the whole shell of it is explosives. Inside is a big lump of fissionable material, unstable radioactive stuff like plutonium or something like that. Okay, you detonate the explosives on the outside and suddenly a whole bunch of particles go flying in at this unstable material. And when they strike it, the atoms start to split. Okay? And when they split, the pieces of them go off and split other atoms, and you get this chain reaction that runs away and turns into a giant mushroom cloud obliterating civilization. Yeah? Okay? That's how a nuclear bomb works. All right? So you basically just get, okay, the explosive particles, okay, coming in and causing this fission to happen. Obviously that's a simplified, dumbed down version of how it works, but okay, that's essentially how it works. Now, the other kind of nuclear power is fusion. Okay? Fusion's how the sun works. All right? And what you do with fusion is you force atoms together. That's much harder to replicate on Earth. Okay? Because you need huge amounts of pressure and forces that will force two atoms together. So the most common fusion reaction would be to take three hydrogen atoms and force them together to make one helium atom. Okay? And in this process, you physically change the structure of the atom. Anytime you physically change the structure of an atom, you have some sort of nuclear reaction. Okay? Whether you're splitting it with fission or whether you're causing it to join, okay, through fusion. And with fusion, it's quite a bit more complex. You actually, in some cases, turn protons into neutrons and things like that. Like, it's a very energetic process, which is why the sun can generate so much energy. Okay? The bigger a star is, the bigger the atoms it can force together. Okay? Our sun is probably never going to get past helium, really, okay, because it's not all that big. Okay? Much bigger stars are capable of producing much bigger atoms. All right, so structure of the atom as we currently understand it. There's a dense positively charged nucleus that contains neutrons and protons, and there's a large volume of space surrounding the nucleus in which the electrons can be found. Okay? So in fact, atoms are made of a lot of empty space. Okay, so this is a picture of what physicists and chemists believe the orbits, or what we call orbitals, of electrons look like. Okay, they're not really orbits; they're not circles. Okay, that's why they call them orbitals. Okay, an orbital is an area where you could find, or are likely to find, electrons. And the further away from the nucleus the orbital is, the more energy it contains. Right? So when we're talking about fluorescence, it takes a certain amount of energy to make an electron jump from, let's say, this orbital to this one. Okay? Once you get over that, it makes what's called a quantum leap, okay, into the next orbital, okay, the next level up, okay, and so on and so on. And then when they come back down, that energy gets released. Okay? All right, the other thing we really need to know here, okay, is that physical properties are determined, okay, by the different numbers of protons in the nucleus. Okay? Different numbers of protons in the nucleus is what makes up the physical properties of every material. Okay, questions on that? Everybody's good with that part? Okay. All right, we've got a few questions I'm going to want you to answer here. Okay, I'm going to give you guys a handout that's got them on it so you can write right on it. Okay, and we'll give you some time to go through those, and then we'll go over them as a class before we start moving on to the next thing. Okay, so I would say you probably want to have, reasonably complete sentences here for these so that they're useful to you when you're coming back to study them. This is pretty much the same stuff that'll be like quiz material or multiple choice question material on a unit exam. Okay, that kind of stuff. Candy, can I get you to turn that light back on for me, please? Thanks. Okay, I'll give you a little bit to get those answered here, guys. Okay, so for our first question here, the idea of the atom was first proposed by whom? Democritus. Okay, why didn't people like it? Okay, there was no way to prove it. It was kind of complicated, and there's one other reason. Right, everyone liked the four elements better, okay, because it just made more sense to them, right? It was something they could understand. Okay, for number two, what elements did the Greeks believe all matter was made out of? Fire, water, earth, and air. Yep. Okay. Why was that a logical conclusion at the time? Well, I mean, you could very simply look at stuff, right? I mean, if you looked at water, water was water, okay? But when you heated it up, you combined water and flame. Well, that means that steam must be some parts water and some parts fire, okay, and so on. So they had, it made sense. It was easy to use. All right. Number three, during the Middle Ages, what group of people inadvertently did a lot of work to develop the science of chemistry? Candy? The alchemists, what was their goal? Right, common materials into gold. All right. Number 4, late 1700s, a man used the data from many experiments on matter to develop an idea on the structure of matter. Who was he, and what were the points of his theory? Right? Right? Mm-hmm. Right. Okay, so first we've got that everything's made of these tiny indivisible particles. Okay, each element has its own unique atoms, so atoms of different elements are different. Okay, and then the last two parts about kind of the behavior of matter. All right, atoms can go together in simple whole number ratios, but in a chemical reaction, they themselves are not changed. All right, so it's always good to kind of put that in your own words and solidify it in your mind as opposed to copying out exactly what's down on the notes. Okay, because that means that you've had to process it and you're more likely to remember it that way. Okay. All right. For number 5, looking at this theory now, what things do you know of that can prove some of his ideas wrong? Okay, we know the solid sphere model's not right. Okay, that's one of the things. Right, okay. We can split atoms, okay, given the right technology. And in fact, some very large atoms kind of do it on their own at a slow rate. Okay, so yes, while most atoms effectively are indivisible, it is possible, okay, for certain kinds of atoms. You're not going to split, you know, a hydrogen atom, because you can't. It's as small as you can get, all right? Things like that. All right, number 6. Describe in your own words the models of the atom discussed here. Give a brief explanation as to why each has been rejected or changed over the years. Do you think our current model may change, and why? All right, so just quick summary here. We started out with solid sphere. It was rejected because it couldn't account for the movement of charged particles. Okay. Then we had plum pudding, which kind of accounted for the movement of charged particles, but didn't account for behavior of atoms in chemical reactions, and you know, the whole proton and neutron idea was kind of not there. Okay. Then we had Rutherford's model. Okay. Rutherford's model had all the electrons essentially the same distance away from the nucleus. All right. You could see them. His model kind of looks like your stereotypical physics symbol. Okay, so all the electrons kind of go like that. Okay, and they're all the same distance away, just at different angles. The problem with that is it doesn't account for the energy movement of electrons. All right, Bohr's model said yes, some electrons have more energy than others, but his was too rigid and didn't account for them being able to move and change energy. That's why we got to de Broglie's electron cloud model, okay, which is the one we accept now. Okay, is it likely to change? It's possible. Okay, it's possible. We're discovering all kinds of new things about the behavior of the atom and all kinds of subatomic particles, okay, that protons and neutrons are actually made up of, okay, like all the different kinds of quarks. Okay, there's up quarks, down quarks, strange quarks. I can't remember. There's all kinds of different quarks. Anyway, it's made up of these smaller things. Okay. Number 7, as our knowledge increased, we discovered the atom had smaller parts. Okay. Those parts are electrons, protons, and neutrons. Which two are in the nucleus? Neutrons and protons. Protons are positive. Electrons are negative. Okay, neutrons are neutral. All right. 1 cubic centimeter of lead is much heavier than 1 cubic centimeter of carbon. Okay, why do you suppose that is? Right, okay. Yeah, from an atomic standpoint, lead atoms are bigger. Okay, so if I have a cubic centimeter of both, lead is going to be heavier because its atoms are bigger. But there's also the even easier answer to that, which has nothing to do with the atom, and that is that lead is more dense. Okay, I mean, water is more dense than carbon. Okay, so it's all a matter of sometimes the structure of things too. All right. For number 9, nuclear reactors use atoms with very large nuclei like uranium, which has 237 or 238 or 239, depending on which isotope you get. Okay, particles in its nucleus for fission. Why wouldn't they use smaller, less dangerous atoms like lithium, which only has 7 particles? Yeah, smaller the atom, the less energy there is holding it together. Yep, it's more stable, it's less likely to split, and it's a smaller target. Okay, I mean, we're talking about trying to split things that are incredibly small. You want to use the biggest incredibly small things you can find because you're going to hit them more often. Okay, all right. Number 10, atoms are indivisible. Okay, we kind of already talked about this. We know that statement's not entirely true given proper human technology, okay, because we can obviously shoot small particles, okay, at atoms and cause them to split if we're using the right atoms. Okay. All right, number 11, from what you know of the structure of the atom, why do you think or how do you think the atom stays intact? Why do the electrons not fly off or the protons separate from the nucleus? Right, electrons are attracted to the nucleus through electromagnetic forces, okay, and so they stay there. All right, and we talked about the glow-in-the-dark materials already, so you kind of have the answer for that. Okay, tomorrow we will be moving on, right, to just an AP lesson, actually, talking about atomic structure in more detail. Questions? Yes, there will be a quiz on Thursday. Sorry, we're not doing that tomorrow. Tomorrow we're doing the Google Classroom stuff and then moving on. The join codes are up there on the board now too if you wanted to join on your own and know how to do that. Okay, the join codes are up there. We're going to be doing it in class tomorrow, so you don't have to. It's just if you're desperate.